Is it expensive? Is it difficult to deal with? You know, what's kind of going on there? So I'll just take you through a few things here. Just some examples of like very recent data, so you can get things very up to the minute. So this is Landsat data, which is a really useful data set, and this image is from about 2 weeks ago. This is Mount Kenya here, and we're in there. So this is I think like 30-meter resolution. You get it every you know, on a time scale of a matter of weeks, and this comes in many spectral bands, more than you can see with the naked eye. So with these spectral bands, you can compute various interesting stuff, like different things to do with vegetation or like what's happening at those places. So that's one useful source of modeling information. So sometimes the things you use aren't the direct pixels that come sensed from the satellite, but it may be some derived data product. So this is NDVI, Normalized Difference Vegetation Index. And so this uses the green and the near infrared bands of imagery to try and compute just how much vegetation there is, like how strong is the vegetation on the map. And so you can download these things here. So this is data up to May the 31st, so up to a few days ago, and this is vegetation strength in East Africa. And so you can download this, and each pixel is 250 meters squared. So that's really useful stuff, right? You can do a lot of interesting things with that. Very, very up to date. All completely free to access, and you know, there's really no obstacle to that. The data sets get quite big. Once you start looking at things of like 250 meters, if you want to do something a whole country, you know, that's starting to get pretty big. And then if you really pull the feed every 5 days, which I think is how often they produce this, pentadals every 10 days. So if you pull this down every 10 days, then those data sets get big quite rapidly, and you know, you need to start doing things on a server. But if you have a focused area, then it's not that big, and you know, really you can do stuff on a laptop. Some stuff which is pretty interesting is weather data, and this is updated so frequently, it's crazy. So this let's see if we can refresh the page here. So you can get images hourly of weather. Now the pixels are pretty huge. Often you get like kilometer square pixels or something like that. So you know, it's not going to be good for sort of counting the, you know, you're not going to see your house in it. But I always think there must be lots of interesting applications of this that haven't been thought of yet. You know, hourly observations of the Earth from the space. I mean, what you can tell right now is that in the area it's cloudy, if you didn't know. But you can kind of see where the clouds are moving. It's quite cool watching these things. So you could go at a more specific level and look at high resolution imagery. So this is 50 centimeter imagery, and this is a refugee camp in South Sudan. This is something we've been spending a lot of time on in Global Pulse recently, is trying to quantify refugee camps from high resolution satellite imagery. Currently they're manually annotated by UNISAT, the UN's Operational Satellite Applications Program, and analysts will click on each of these buildings and produce shapefiles of how many shelters there are in refugee camps around the world. Huge task, very laborious. And so we're looking at trying to automate this. And so you can use object detection methods to work out, sorry, this isn't very clear, to work out which types of shelters are there and where are they. And then this derived stuff can then be the type of data that you can use. Maybe you're not really interested in the pixels directly or the measurements, but you're interested in the locations of different types of objects on the surface of the Earth, and in computing things about that, like the densities of stuff, or is this refugee camp increasing or decreasing, or what's happening. So that's satellite data. Of course, with spatial data, there could be all sorts of stuff. You know, many of you have been out in the field attaching devices to trees and such like. So these are devices with locations, and you know, when you pull data feeds from them, you may be interested in some analysis which takes into account where these things are relative to each other, right? You might want to somehow put that stuff into the mix, and so the proliferation of sensors that we have and things which are geolocated, that's another great source of spatial info. What we're going to look at mostly just now is forest cover and deforestation patterns. And this is this is an example that I've not really worked on before, but just pulled together a few things for the purposes of exposition just now and for practical. It makes a nice practical because there are some great data sets, derived data sets of how much forest cover has been lost year by year. This is the University of Maryland's global forest cover data set. And what we can see here is, I couldn't decide. I was like, should we do Uganda? Should we do Tanzania, Kenya? They're all my favorite. I can't miss out any of them. If I had to, I mean, obviously, if I had to choose one, I was like, why not? You know, let's do the whole chunk. So this is the chunk of those three countries, and what we can see here when you go to the Maryland Global Forest Cover dataset, you can download a map of forest cover in the year 2000, and that's what we're looking at here. So darker shades of blue are where there's very little forest cover, and the lighter shades are where there's a lot of forest cover. Now, it turns out that defining what a forest is actually quite a tricky issue. I think they use some definition which is pretty pragmatic, but has some drawbacks. I think they look at like the amount of vegetation above 5 meters as a proportion of the total area. So that's pretty good. It does mean it probably underrepresents parts of Kenya where there's savanna. You get like acacia trees and so on, and there might be only one every so often, but it's still forest cover and it's still very important in terms of the function of a forest ecologically. But that would be kind of understated by this measure of like how much is above 5 meters in one area, and then it kind of overstates plantation forests or that kind of thing. So there's a few snags, but broadly we can think of this as a measure of how much forest cover there is. And what is even better than the snapshot of the forest cover is the computation which this group have done of looking year by year at where was forest lost and where was forest regained. So the data which you'll find in this package for the practical is a down-sampled version of this. And okay, so it's very difficult to see here, but we have particular areas where forest has been lost, and we have encoded that as the year in which that pixel, where there was significant deforestation. Okay, so we've got data which spans from 2000 up till the end of 2016, and what we're going to be looking at today is how much forest has been lost over the course of those years up till around a year ago, and what are the patterns and what can we predict? So the darker pixels are places that got deforested earlier, and the lighter pixels are ones that got deforested later.
How is reforested? Or is that not an issue?
Reforested, yeah, I didn't include that here. Yeah, there's not much reforestation, unfortunately. Yeah, so it could be that a place gets deforested and then replanted later on. So that's certainly something if you were doing this properly, you'd want to include the potential of that. But that's kind of as an aside, that's an interesting factor here. If it could be that someone kind of clears savanna and then puts like oil palms or something, yeah, and like you might see on the basis of this kind of example that like, hooray, there's loads of forests, Okay, so that's the kind of data. Now, what we also commonly have in this kind of problem, where it's like we want to predict, say that's our thing, right? We want to know what's going to be happening with deforestation like this year. What we want to get to is a prediction of East African deforestation in 2018. So it's obviously useful to know where was deforested before. That's going to be a useful factor. But there's probably a bunch of other stuff which is also going to be relevant. I'll show you a few here, and then maybe we could sort of think about what other stuff would be. One thing which we know is important in this kind of thing is where roads are. So places tend to get deforested near to where there's a road, because if you deforest the thing, I mean, you've got to take it somewhere, right? So if there's a road, it's going to be easier. And you can kind of see that, like, so in sparser areas, indeed, there's kind of less of a deforestation factor. So there's some, this seems like a useful kind of covariate here. And already maybe there's some questions in your mind about like, okay, these roads are defined as like line segments and longitudes and latitudes, how, like, what are we going to do to predict like locations on a map? So that's roads. Like another thing which I thought might be useful is which areas are protected or not. Like if something's inside a forest reserve, then it's probably less likely that, all other things being equal, that the trees there will be cut down than if it was outside a forest reserve. So if we look at where the reserves are, so interesting, there's many different types of protected area, right? So we're using some data set, which I've linked to in the notebook. I forget the details. Protected Planet is the website where you get these. And so you can find that like for one area, it might be protected in several different ways. Let's have a look at some of those. I'm using QGIS here, by the way. If anyone is wondering about this, if you're doing any kind of spatial exploration, then it's really useful just having a good, knowing your way around a GIS tool. Because if you try and just plot things in a notebook, and then you're like, I want to zoom in on that bit, and you have to sort of spend a minute, like, okay, 300 to 500, and often you just want to be able to switch off layers on and see how things interact. Okay, so we can see that there's different types of reserve. So this one here is a national park, Serengeti. Okay, so there's like Ramsar sites and various different designations, and so it might be that some types of protected areas are like more protected than others. That could be a factor. And so I guess we'd hope that there's at least less deforestation, and you can kind of see that there's less deforestation in protected areas. Not zero though. I mean, you can certainly see this is a whole interesting thing in itself. Like of places which are supposed to be protected, where's the most deforesting going on? What's happening there, and can we characterize it? That might be an interesting thing to look at. Okay, so those are a bunch of covariates. We also have like where the tree cover is, right? So we can know, like before it was deforested, how much was there? Obviously, there's not going to be deforestation in a place with no forest, for example. So that's a set of things that we could use to build our predictions on. These are sort of things which just came to me as things that might be useful as a practical, but there might be a million other things. I mean, can anyone? What are people thinking of? I mean, there might be a bunch of stuff we're missing here that could be good covariates. What other stuff might you pull in? Population density. Well, that would be a great start. Yeah, exactly. So maybe the roads is like slightly a proxy of that, but I'm sure the population would. Yeah, there might indeed be extra information in knowing where the population is.
Nearby deforestation. I know it's a bit harder. It's not exactly
Nearby deforestation. Yeah, sure. Well, that could be fundamental, right? That's probably the most.
Deforestation or something like that. Locations.
Mm-hmm. Mm. That's an interesting point. Yeah, I mean, maybe if there is a lot of farming going on next to an area which is forested, then perhaps there's more human pressure on the forest area. Yeah, absolutely. As opposed to an area which is non-forest, but it's not being used for agriculture or it's not residential. Yeah. Mm-hmm. Mm-hmm. Yeah. Yeah, that's an interesting point. Right. So maybe. Perhaps we're thinking of this like year by year, there's like the same relationship, you would, like perhaps overall the environment is changing and maybe we need to know how it's changing to get the best prediction. Yeah, I mean, perhaps there's something like that, yeah.
So, do we know why it's being deforested? I mean, in Oregon, we would be cutting down trees for timber. In Brazil, they might be doing that, but also clearing land for cattle or for other farming purposes. Other places near a refugee camp, maybe it's just for firewood.
Mm-hmm.
So, I mean, and then yes, maybe they're just spontaneous fires caused by climate whether, what are the reasons, I mean, do people know what the reasons are here?
Yeah. Say again? Urbanization, yeah. Maybe need for fuel. I mean, a lot of people cook with firewood, right? So charcoal burning, yeah. Clearing land for construction, yeah.
So what's the answer? Which one is it?
For every tree in East Africa, why was it deforested? These are all good points. Yeah. So I should say that I'm not at all an expert in this. Don't get the mistaken impression that because I've talked about deforestation, I really know all that much about it. It just sort of was an interesting example that I pulled together for the sake of this talk. Yeah. Okay, so that's a few. These are all great things you could pull in, and certainly there are data sets readily available of human population, of land cover, so you could get some assessment of which lands are agricultural versus other types of things.
So when you're talking about like search about more all the data sets that we, for example, if I need to know population, I need to know like if I need to if I need to know like certain information, I know what database I need to go, right? But in terms of spatial data, it seems like I have my doubts. For example, if like let's say I need crop data, right? I found soil that the university in the US provides or has data sets that is needed for me, right? So I always have my doubts if the source is reliable. Like how could it like what is conventional data? Like I know what is the spatial data. Like is there any raster for you? Like what they use?
Yeah, I see. So like in terms of knowing what exists and what reliability.
Not every source provides every force, but all agree on the default.
Yeah. I mean, I don't know that there's anything sort of unique to spatial or satellite data in that. I mean, I suppose if I was trying to assess reliability of a source, I would sort of look up the main reference and sort of look through the paper and see if it looked like good methodology or extensively tested or not. But yeah, it's there certainly is probably some degree of variation in some of these things. Like for example, this is an assessment of like forest cover based on Landsat. Like from a few spectral bands, they've tried to estimate where's forest and where's not, and probably that goes wrong a bunch of the time. I imagine the answers are like in the references somewhere. They've probably sort of done their evaluation, and you can look up the stats. Yeah.
I guess maybe to find a secondary source that's literally ground truth on the ground. So hopefully could have checked probably whether trees disappeared. So that would be the way to check. You might want to check in different types of forest then as well. So you are making sure you're not extrapolating.
Yeah.
Last question. All this research, it seems that many special data sets are so outdated, so let's say over the culture, I guess most of them in America are dated to 2000. So I mean, I guess like in 16 years not much changed, but 16 years is already such 70 years. I mean, like my question is also about like what is kind of again like speaking of more population, right? I don't know like use World Bank population estimate of 2000, so different time to time for depending on the purposes, but like I will say this is the most updated, most recent one. But in terms of expression data, like is there kind of I guess it depends on what data set is for the culture. 10 years will be still fine, 20 years will be still fine.
Yeah. So.
And if you don't have, what do you do? So like, machine learning, like what do you do to get your data set?
Yeah, so in terms of the timeliness or the freshness of spatial data, this is one of the things I like about data sets derived from satellite is often the revisit time is measured in days or weeks or depending on what you're looking at. I mean, there are portals to, maybe this gets a bit closer to your question, where you can where there are many things combined in one. So like the Google Earth engine is one where you can, that's a sort of standardized interface to many of these different data sets, which kind of updates when new stuff is available and all of that. But it's true that for some of them, especially where there's a component of calibrating with ground truth, that it gets really scarce. So like world population data, I mean, there's the world pop data set, which is a great data set, but often that's relying, I mean, when we look at Uganda, for example, the data that world pop is relying on is the 2002 census, as far as I know. So it's like extrapolations based on a 16-year-old data set. Yeah. So, you know, and I guess the issue there is they have to calibrate with ground truth, with like census data and so on. So where there's something which is like purely satellite, then you can have much fresher data, but then you have this issue of like, is it well calibrated? And then your point about like, how do I know if it's really real? Maybe it's like, it comes up fresh. It's like, you need more data. Yeah, we've got new data, sure. But then is it that it's sort of diverged from the ground truth in some way, or yeah. Okay, well, let's see how we would start to get into this problem of predicting the deforestation. We want to predict like next year's deforestation based on all the stuff that's happened in the last 16 years or so. So we're going to have to start by dealing with the fact that this data comes in different forms. If you download some spatial data, it may come as a raster, which is like this. So it's like a grid of pixels. When you zoom in, you see the pixels. Each pixel occupies a certain area on the surface of the Earth. And then there's other stuff. We've got a bunch of different types of things here, which is why I threw it together into this practical here. So we've got roads, which are defined as lines. So these are segments with like longitudes and latitudes between them. There's things like the protected areas, which are polygons. So there's a whole load of different stuff going on in there, and we have to somehow combine them together. So let's look at that. All right. So when you start, what I wanted to do was talk through some of the ideas in the notebook, which you'll be looking at in the practical later. And the purpose of the notebook is to get up and running with a prediction model, which is super simple. It's like an embarrassingly simple model. The main aim I had when writing this was to get something that I was fairly sure would run on most people's laptops without any exotic libraries and so on. So it's pretty sort of simple methodology. We'll get you a prediction of deforestation, which actually maybe isn't too bad. And then we'll sort of think about, like, of the simple model, you know, what ideally would you have in a model, you know, if you really had more time and computation to bring to bear on it, you know, how would you kind of extend it from the starting point? So one thing we've got to do fundamentally is deal with these different types of data. Like we have to predict areas that we think are going to be deforested, and the covariates that we have to do that prediction are all different types, lines, polygons, and all sorts of stuff. So, you know, before we even get into formulating a model where we write down some predictive process or something, like we've got to in some way be able to deal with it. So I've written a few functions for you here to read in these different types of data. And what I've done is, just to save a bit of time getting you up and running, is to convert them all into raster data of the same corresponding grid. Okay, so we have this grid of like where were the trees in the year 2000, and where were trees lost. So these kind of live on the same rectangular grid. So I've converted all the other stuff into that as well. So the roads, what I've done is coded the pixels 1 or 0, depending on like if that pixel intersects with any road anywhere. So it's 1 if it intersects with a road, 0 if it isn't. Same with the protected areas. So you can read those in, first of all, as a bunch of matrices, which encodes the positions of different types of features. Okay, so when you look at this, the first thing you realize is it's quite difficult to actually even visualize. If you look at the loss in a particular year, So this is pretty difficult to see even on a laptop screen, and it's basically impossible to see on a projector. So there's tiny like spots here, encoded as ones, where forest cover was lost in a particular year. So I've written this this function here, loss in year. So if you want to get the forest loss in the year 2010, then you can call that, and it will give you back a matrix corresponding to this area of East Africa, and zeros, which is this dark purple, and ones, which maybe some of you with excellent eyesight can, you know, the younger ones, can sort of make out that there's some pixels which are switched on there. Okay, with precisely the locations which were deforested. So that's yeah. Okay. Yeah.
But which function is that? Is it in this function? All these functions
which function is it? It's a function. Okay, it's a function here. It's actually really simple. So all it is there's a library called raster.io. I always pronounce this in my mind as like rasterio. Sounds like, you know, enter rasterio. So there's a function called mask, which takes polygons or lines or whatever, and can use that as a mask on a raster grid. So you define where your grid is, and then you say mask it with this, and then turn everything inside that mask to ones. So it's like 3 lines of code like that. Okay, so we've got some points here. Now, those are specifically the points where there was deforestation. So let's say what we're trying to do is like take deforestation from one year, and we're going to try and predict what the deforestation was in the next year. Okay, so we're going to try and take this 2010, we're going to try and predict this 2011. Another pattern of like tiny dots on this landscape that you can't see, and even I can barely see looking at this thing here. Okay, so that seems kind of tricky. But let's think what our intuition is here. One of the basic things we could use to predict is the fact that if something was deforested, if that tree was cut down over there, then I would say the next year, like that tree might be kind of at risk, higher than average, you know, whereas a tree like 100 miles away, I don't know. Okay, so there's maybe some concept of like if stuff happened nearby, then that's more strongly related in some way. Yeah, that might be one principle we could use. Actually, can anyone think, maybe we should just sort of kind of brainstorm here a bit. Like does anyone have any ideas they might use to do this prediction in general? Say this was say you got back to your you know, your home institutions and so on, and at your work they say, I've heard you've been to this great Data Science Africa training session. You know, you must know all the stuff now. We want you to predict deforestation for next year. What do you think you would start off with? Any ideas? Yeah.
I think one of the main things to look at is the reason why deforestation was done in the previous year, so that you can be able to predict for the next year. Because these places might be close, but that doesn't necessarily mean I want that kind of a tree to be out.
Yeah. Okay, so that's definitely going to be a fundamental thing. If somewhere, like whatever happened last year, it's probably going to guide us on what happened this year.
Yeah, the reason for that might be.
Yeah, the reason is, yeah, exactly, as Tom was saying. Yeah, why was it deforested? Yeah, sure. Yeah, that could be interesting too. Okay, any other thoughts, like principles or ideas that we could use to yeah.
I'd want to see the settlement patterns around the area. That would be a great pointer to what to expect next year. There's more houses, and the kind of houses being put up. Not all kinds of people continue deforesting. Or some people are clear to settle, build mansions, etc.
Yeah.
Others maybe more low income kind of settlements will settle and continue.
Yeah.
There. So I'll watch more that. That would be good.
Yeah. Okay, that's interesting, right? So if we had data on where settlements were, then we could try and use that to predict deforestation. I wonder how we would bring that into a prediction, because if you say you had the exact position of like every house in East Africa or every building, then like you're not going to have deforestation exactly where that house is because there's a house there, right? Like so in some way, you're going to have to take, if we had that information on exactly where the areas settled were, then we'd have to bring in maybe not the positions of the houses themselves, but like we'd have to maybe compute from that, like which are the areas at risk.
There's a correlation. Even if they're not exactly where the trees are, but the proximity between where the houses are coming up and the kind of houses.
Yeah.
And what's happened to the trees tell you what to expect next.
Yeah.
So even if they're not exactly where the tree was,
Yeah.
we could correlate the distances.
Yeah. Yeah, excellent. Okay, so I like that. Proximity to the houses is probably a key kind of factor. So and in the same way that it might be a factor for deforestation as well, the previous year, right? Like if that tree's been cut down, then that tree's already been cut down. It's not going to be cut down again. But maybe the one next to it is kind of at risk. Again, there's going to be this proximity factor. And in the same way as the houses or last year's deforestation, we're going to have to think like what kind of range of proximity are we thinking about? Like if it's right next to it, then that's probably quite significant. If there's a tree right next to a settlement, then that's important. A tree a kilometer away from a settlement, is that at risk? 10 kilometers, 100? So there's going to be some idea of like, there's going to be some range of proximities which are like relevant, and at some point it stops being relevant. So if that tree was cut down, then like that's grave consequences for things which are like 10 meters away, and a bit less serious for the things 50 meters away, and a bit less serious again for the things 2 kilometers away, right? And like somehow as part of this, we're going to have to work out like what does proximity mean in this sense for these different things? Can we use?
Like historical growth rate, like growth rate.
Oh, historical growth rate. Oh, right. Okay. Yeah, right. So we could have another spatial prediction of like where do we think the settlement is going to be, right? So we could say like models within models. Yeah, we could say like here's where the settlements have been year by year, and they're expanding this way, and so we think the settlement's going to be like that, and so based on that, it's going to become proximal to this forest area over there. Yeah, I mean, absolutely. Yeah.
And the type of plants that are being removed, maybe people are coming after institution from this.
Yeah. Sure. Exactly. Yeah, if there's, there could be all sorts of reasons. Yeah, that's one of the tricky things, isn't it? There might be many things going on in practical terms. Other ideas? Yeah. Yeah. Okay, so if there's things that we know are going to happen and we think we can connect that with deforestation, then maybe we can build that into a model. And I guess what we have to do to be able to do that is to have some way of expressing what the relationship between that is. If we know that like this is an oil area and there's going to be certain types of activities there, then we ideally want to be able to write down in some way, what's the relationship between a place being an oil area and what we think is going to happen. Like, I guess we're going to have to start thinking of, we've got all these different types of information, and we want to make our prediction, and we're now going to have to see how all those different data types can be combined to actually make the prediction, right? So we've got this one concept of proximity that's pretty useful. So things near to other things, like that kind of tells you about the risk, or they're related in some way. Let's think about this this proximity issue. I want to show you some plots, and I'm going to not tell you how I did them, and because there's actually many ways of doing this same type of stuff. Okay, here in this, another of these basically entirely dark rectangles that you can't really see anything on. I wonder if it'll let me. No, it's too clever. Okay. Here is like the exact positions of some areas which have been deforested. So these are tiny, tiny pixels, and there's like a clump of them over here that you can't quite see, and another couple of them over here that you can't quite see. And they're the precise locations, deforested areas, like little squares on the ground that have lost forest cover. And what I've done here, this is something which I've produced from this. I've kind of like smooshed it out in some way, so that now it's a bit easier to see, right? That there's some concentration of area that's been deforested there, and there's another. We can start to kind of get a feel for like which areas have been deforested, and now that I've done this, it's a bit like what happens when I take my glasses off, and everything sort of blurs out. It's like I've kind of lost the detail of like precisely where things happen in a way that the stuff is blurred together, and in doing so, like you usually think of like making things blurry as something that loses detail, but actually on the contrary, this seems to like pull out some of the spatial patterns in a way that's a bit difficult to get from just looking at the points. And by doing this kind of like smooshing, blurring, kind of merging things together kind of process, that's actually building in some idea of this proximity, right? Like we know that if a place was deforested, then places near to it are at risk. Places further away we don't care as much about. So actually maybe there's something kind of fundamental going on about this type of thing. So any thought? There's actually loads and loads of ways of going from something like this to something like that. So any thoughts? What would you do? You've got points and you want to come up with a sort of blurry, merged together kind of idea of where things are, where the areas are. There was a voice. Yeah. A heat map. Yeah, it's kind of a heat map, isn't it? Yeah. That's sort of the result that we've achieved. It's in fact, yes, it's a heat map. So procedures, mathematical procedures from taking these like points here and coming up with there. Or maybe if you can't think of a whole method, like is there any sort of principles that you might use or any sort of mathematical ideas that might help you sort of go from that to this? Yeah.
How about in generating the first image? You go out the place which is most affected, and then
Crop out the place that's most affected.
right now we have an area which is, but if we just crop out the most affected places,
Mm-hmm.
then we can maybe expand it more and then focus on that.
Okay, so how would we calculate those most affected places? Because here we've got a load of points, right? So we've got like exact locations of each of the.
What I mean, we have like a threshold.
Mm-hmm.
Threshold, maybe we have like maybe in a particular location, maybe if we are below or above it, the threshold, then we can calculate.
Okay, interesting. So so how would we compute that threshold? Because here it's either 1 or 0, right? It's like that place exactly was deforested, this place was 0. So if we threshold this, then we'll just get this again, because everything here is either 1 or 0. But maybe we could do something where a threshold comes in. I think I kind of see where you're going with this, yeah.
Is it like you have the count of the population, so the population is plus, you just cut out a particular square and then
Okay.
so the ideal thing, but if you targeting a particular species, maybe get to know where it's concentrated, and then you cut off equal sizes.
Yeah, sure. I see what you mean. Okay, so something like we could take like a bigger grid. It's like a bigger grid composed of these small grids, and then for each area in here, then we could maybe count how many.
That's when we are computing the threshold.
Yeah, that's an interesting thought. Okay, so we could. Well, one way to. So one thing we could think, one way of maybe getting a kind of like coagulated version of these points is this idea of taking areas and like summing up how much deforestation there was in each grid cell, right? That would be one way of doing it. So say we had this square here, and we counted up how many deforested positions there were inside that, and then that whole square could be represented by like the number of deforestations, something like that. So we could maybe have like represent this as like a grid, a coarse grid with like the total deforested area in it, and then maybe we could choose the yeah, another idea.
What about cluster?
Cluster. Oh yeah. Okay. Yeah. That's the point. Sure. Yeah. Why not? I mean, you could. Yeah. There actually are some kind of clusters emerging. So you could say. Let's find only the cluster centers. Yeah, and then maybe it finds that there's a sort of group here and a group here, and we say, okay, there's a cluster there and a cluster there. Yeah, sure, you could totally cluster it. I mean, you might miss out, if you did that, you might miss out on the things which aren't in clusters. So these points which are elsewhere, you may miss out on. But yeah, sure, you could do a clustering with many clusters and then sort of plot where those clusters are. Yeah. Any other ideas? So this, however I've done this, whatever magic technique I used to go from this to this, it wasn't either of those two, right? Like it's not, there's no sign of like a bigger grid here that I used to like compute things with separate areas. I didn't do clusters. So there's some, in fact, there's like a whole range of methods which could be used to get this kind of thing. Martin?
Yeah, I want to give it a try.
Sure.
What if we color each pixel with a value for the number of pixels in a particular radius? So, if for example we looked at, we colored the pixel with the number of pixels that show deforestation in a radius of 5 kilometers.
Yeah.
So we'd expect to have some very bright, and then others with,
Yeah. That's an excellent suggestion. Did everyone pick up on that? So Mark's suggestion there was like maybe to go from this to this, we could take each area and think like how many deforested points were there within, say, a 5 kilometer radius? Yeah, so if it's a place like this where you can't quite see them, but there's lots of kind of points there. So if you're trying to work out what's happening there and you draw this circle of 5 kilometers around it and you add them all up, then it's going to be a big number, lots of things within that. And so that's an interesting idea because then you will get this smoothing out area, right? The smoothing out effect. So yeah, you could do something like that to say to go from this to this, and you could do variations on that, right? You could say like, what's the distance to the nearest area of deforestation, or a few things like that. What I did is actually simpler than any of these things. It's easier. It's not more complicated. Tell us. Okay, you're like, yeah, enough. Okay, what I've done is I did a convolution with a Gaussian. What it is, it's actually almost the same way that heat maps are drawn when you get like web plugins that take points and generate heat maps. For each point here, I've added a blob to this image. Yeah. So like we start off in the top corner. Sorry, this is a bit faint, but like there's a point here. So I've computed a Gaussian at that point with like a high value in the middle and then kind of tailing off around here. Yeah. So it's like so if this is like 0 on the background, then maybe it's like sort of some value there, like 0.1 or something in the middle of where that point is, and then it sort of slopes off on each side. And I do that for every single point here. Every time there's a point, I add on the corresponding numbers of a Gaussian blob onto this thing here. So simply, this is a two-dimensional convolution. We're convolving with like some little matrix which just has a peak in the middle and it sort of tails off to the sides. And that has the effect of kind of smearing out each of these data points. And when you get lots of them together, then they all kind of join in here. It's a bit of a related idea to what you're saying, Martin, actually, but just it's got this sort of smoothing off. Instead of being a hard cutoff at like 5 kilometers, it sort of smooths off. Okay, so that's how I did it, but there's actually other ways of doing it, and I'll give some references to it later. But that's a really simple thing you can do, which has the virtue of running in like a few microseconds. Some of the methods I'll talk about later, which run this, which are better in terms of like the insight you can have into the model and the number of things you can tune and things like that, but do take a bit longer to process, so a bit more difficult to do in practical. But this is really fast to run. Okay, so having done that, that's a pretty simple operation. It's I found a fast implementation of this in SciPy. There's a Gaussian filter function. So what you can do with any of these methods, you can always specify this length scale, right? There was this idea of proximity. Keep coming back to that. How close is close? So if you think about it, we might want to say, if a tree is cut down, then that only matters to things right next to it. And anything which is like more than 100 meters away or something, completely irrelevant. Yeah? And so then we might want to have a small length scale. So you see what we've got here. I hope you can make this out at the back. But when I reduce the scale of this Gaussian, these Gaussian blobs that I added on at each point in the image, then we get kind of something that's a bit more like points around each of the original data points where there was something happening. Yeah. Or we might say that like actually length scales are really big, and like if a tree is cut down here, then that still matters for something 50 kilometers away. So we have to choose what that scale is. And so the more we do it, depending on how we think things nearby affecting other things are, that determines what we choose as our scale there. But probably we've got to set this, right? Like maybe we can't really just kind of guess something off the top of our heads. Maybe we have to kind of compute the right answer in some way. Okay, I think I had it around.
Seems like there's a lot of deforestation in Tanzania.
I know. What's going on, Tanzania? I mean, there are a lot of forests in Tanzania as well, so like, I don't know. I don't know, yeah. Yeah, interesting, yeah. Can put that in context, actually. It's like if you look at the tree cover in East Africa, yeah, like loads of it's in that area. So it's kind of like starting off from more, but yeah, indeed, these.
So what you're saying, the best way to avoid deforestation is to drop down all the trees?
To have no forest, yeah, exactly. Can't deforest if you don't have any forest. Okay, so, all right, so I've kind of been laboring this point, and we've kind of been on this thing here. And this is like a smoothed out estimate of like where's the higher density of deforestation. And the reason I've kind of been laboring this point, partly because it ties into several ideas from what Neil was talking about earlier. Also, this thing here could immediately be used as a prediction for what's going on next year, right? If we simply made an assumption that like what deforestation happens next year is related only to what was deforested this year. And we just said that if there was an area of concentrated deforestation, then we predict more deforestation in that area. And if there was a place with no deforestation, then we predict no deforestation in that area. Yeah, like that could be a starting point for a predictive model. Just like what happened last year, smooth it out a bit, and like maybe that will happen again this year. So we predict that. So what we can do is actually test that prediction. So there's some code here which you'll see when you run through the practical. And basically, this sets up a prediction with the actual ground truth. So the some random extra code, which Mike helpfully deleted. So we've got the thing that we're trying to predict, which is like the loss in some target year, and that's the precise locations of forest loss. And we're going to try and predict that from this kind of density, this sort of smoothed out version of what happened in the current year. And we'll just see if we can do that immediately, like without really any clever machine learning or really any learning of any kind here. We'll just see how well that prediction works. So because this is very simple, it's very, very fast to run, so let's do that. And this is our ROC curve. Did you already go through ROC curves? Does everyone know what an ROC curve is? Yeah. Okay, good. So we're looking at the performance of this prediction. We've predicted deforestation in the year 2016 based on what happened in 2015 only. None of the other stuff was roads and where the trees actually are or any of that, blah, blah, blah. It's just simply that. And that's actually not bad. Like 0.84 is a somewhat respectable ROC curve area. So to interpret this, we've got true positives against false positives. So you could think of this as saying, okay, we could predict the locations of 80% of the deforested area with only kind of a bit less than 30% false alarm rate, which isn't bad, right? A random guess about each location would be along this line here. So if we were able to work on our models to the extent we had a curve going up here, that would mean you were able to perfectly predict every precise point where there was deforestation with no false alarms at all. That would be like the perfect classifier. That's probably pretty difficult. We're not surprised that our curve doesn't quite get up to that level, but the more we get up there, the better. Okay, so that's a prediction, and it's actually not bad. And all we've done is just kind of use this concept of proximity, right? Like, so we had all these other ideas we've looked at first of all, like where are people, what's going on year by year. We haven't used any of that stuff at the moment. We've just used like what happened last year. So let's think of some of the other stuff. We could do the same thing as we did for the density of deforestation, and we kind of smooth that out. We can do the same thing for roads, yeah? Because we need to do something a bit like that. We know that there's not going to be any deforestation exactly on a road because it's a road. It doesn't have any trees on it. So we're going to say, we again have this concept of like stuff near to roads is more at risk than stuff that's not near to a road. And if there's lots and lots of roads, like these places where they all kind of, we've got Kisumu and Nairobi and so on, where there's like lots of roads together, then it's really roady over there. We want some measurement of roadiness. And so by applying the same operation here, which I've used this very simple method of a Gaussian convolution, but there's better stuff to look at, just a bit slower, you get this kind of result here. So this looks like a useful covariate, I would say. We've got this measure of roadness, and that's probably a risk factor. And we've got like various other things as well. Similarly, we have a corresponding grid here, raster grid, of like where the trees actually are. So in each year, we can compute like what was the forest cover that year, and then that's also probably a useful predictor. Like the more trees there are, maybe the more likelihood there is a tree gets cut down. So somehow now we've got to build a predictive model. Before there was no prediction, there was prediction but without any learning. Like I just picked a kind of length scale from the air and made some predictions with it. But now we've got covariates and stuff, right? We're probably going to have to learn in some way how these things relate to each other. Any ideas? No ideas yet. one thing to tell you is that it's not, although this is laid out spatially on a grid, there's not really fundamentally anything different doing than any other type of prediction. So if we were predicting like the quantity of deforestation, if it was like a number at each point, like the number of tree or the percentage of place cut down, that would be a regression. But here it's even simpler than that. We're just saying, like on this grid, the thing we're trying to predict is points. It's probably easier to see that on. The thing we're trying to predict is for a particular year, like the exact locations where things were deforested. So it's actually a classification that we're trying to do. Like for 2016, what we have to do is try to predict for each of these points on the map, like yes or no. Do we think it got deforested or not? Or maybe like a score or something for each point. Like we want to say, this one, I'm sure, you know, that place definitely, I think it's been deforested. This place, I'm sure it didn't. Maybe other places were kind of a bit less sure. Okay, but it's a classification, ultimately. So what I want to convey to you with this next bit of code is that it's the same type of computation as you do with other things. So you can build in all sorts of like clever spatial ideas, but you don't have to, and that's what I'll illustrate here. So I'll show you this last example, and then I think we'll take a break, and then it's over to you to have your turn. What I've done in this next section, prediction with covariates, is I set this up as a classification. I've done this in an embarrassingly simple way, just to get something working here. What I've done is taken the so we're gonna have some training now. We're setting up some kind of predictive model, and we have to learn something. We're going to set some parameters from data, which we didn't before. And what I want to do is take as training the year 2015 and 2016, like learning the relationship between 2015 and 2016, and then we're going to try and train on that and apply it to 2016, 2017. So any temporal relationships, spatial temporal relationships, we're going to hopefully try and kind of get them in some kind of classification model, and then put it into action and see how well it works. Okay, so all I've done here, really simply, the purpose of this is try and make you not be scared of spatial predictions. It's just a classification. Maybe there's like lots of stuff you're trying to classify. If you have a grid of 1,000 times 1,000 pixels, then you're trying to classify a 10,000 dimensional variable, but that's fine. So what I've got is a couple of, I've got the loss density from the previous year, which is this kind of blurring thing I did here, this Gaussian convolution. I've got road density, same thing, and all I've done here is made up a feature vector with like how much deforestation was the year before, what's the density of roads, like are there protected areas or not, and to what extent was the tree cover at that place. This, I think, is a number between 0 and 100. And I've like put them in a column which represents, every row represents one pixel of the original image. So we've got loads and loads of these. We have about 700,000 examples to train from, which corresponds to every single position in this grid. And for each one of those, for each position in our grid on the map, we have like the density of the loss the year before. We've got the density of like how roady is it. We've got like whether it's a protected area or not. And we've got how much tree cover was there the year before. And each pixel is now a training instance in our classification. And the thing that we're trying to fit is like the loss in the next year. So for each of those locations, we've got like, did it get deforested, yes or no? Okay, and we're going to try and train a classifier. And I've trained this here with a classifier that has nothing to do with spatial data. I mean, this is just like a general purpose, like a random forest-based thing that you can. I quite often like this because you can use it regardless of the characteristics of your data. So if you don't know anything about the scaling of the data, or it's got some weird nonlinearities or discontinuities or something, doesn't matter. It's one of those sort of all-purpose kind of things. You can usually sort of run it out of the box and get some reasonable results. But there's certainly a lot you can do better, and we'll talk, I think, in the next session about like what the shortcomings of this model are, like by not including explicitly the spatial relationships and so on. Like, what are we missing with this kind of model? But that said, let's give it a go. If you train it, okay, also I've been trying to write this. The other reason of using simple stuff is that you can run this on your laptop, so it trains in about 20 seconds on several hundreds of thousands of points, and then you can do this prediction, and you get like a new prediction where the ROC has gone up a bit. So now we're doing a bit better. Not doing spectacularly better. I mean, it was like 0.83 or 0.84 or something before. We've gone up to 0.87 by bringing those covariates in. But we're still using a very, very simple model. Okay, I feel like I've been talking for a while, and it's probably time for a break, and you guys are going on to the practical quite soon. Anything people are mystified about or want to ask questions or comment on at this stage before we break? Damon? Yeah, Flavia. My favorite color. My favorite classification algorithm. Oh, geez. I mean, it depends what you're trying to do, right? Like, I suppose if you ask me, like, what's your favorite algorithm, like, for something, then yeah. Deep Gaussian processes. Yeah, can't go wrong. Yeah, I think. I mean. Yeah, I think the only way to answer that question is like with reference to some task that you're trying to do. I would say, yeah. If you have other questions like what's your favorite algorithm for X, then I can try to find an answer.
Okay, did you choose this by random? On some models?
Oh, the gradient boosting.
Yeah.
I mean, this was the first thing I tried. I didn't, I coded most of this like last night about midnight actually. So there wasn't a great deal of sort of sophisticated trying of different models. I often use. There's a few things which I do use like in exploratory analysis of a new classification problem. So I usually try some simple things just to get a feel for different types of problems. So sometimes things like nearest neighbor I would quite often look at just to see like, is it that kind of problem where like the proximity of points to each other according to different distance measures? You know, is it that kind of thing? I sometimes use this in exploratory analysis of how difficult a problem is when, for example, I'm not sure if there's going to be weird issues to do with like the scaling of different variables, and it's late at night and the practical's the next day, and so like, I don't want to get into like, pre-processing on the data and all of that. Like, sometimes you just need a method that can eat anything and give you some halfway usable result. But it completely depends. So for spatial, I mean, knowing that these data points are spatial, like this kind of algorithm here is kind of general purpose. So we can do a lot better than that by using the information that these do refer to physical things in space, and so there are all these ideas of like proximity and density, and we'll get on later to some of the stuff which would be much better for this particular problem. But like, yeah, general purpose exploration. That was the kind of thinking behind that.
How do you do the validation?
The validation. Well, so what we're doing here is like we're training on some data and we're testing on some other data. But indeed, like this, one of the many shortcomings of this thing here, there's a lot of sort of better things to do in terms of the spatial analysis. So one of the things we're doing here is we're not really doing any cross-validation on setting our parameters. So for example, we might need to assess different length scales, right? That's one thing we've not done here. As all the code to this point, that's hard-coded. And so probably we do need some way of like taking like not the test data, but of the training data we have and kind of finding some way to cross-validate. So we try different settings. We also might want to kind of like think about where we're going with this. We might also want to not have two different steps Like one where I've done this kind of smoothing out of the where the loss was and where the roads are, and that's like one sort of data preparation step, and another where I train the classifier. I mean, probably we want some model which combines all of that together, right? So in combination, you find like the overall best answer, and so that would be a different type of model with a different type of validation. But for now, all this is very simple. This is like the kind of starter pack to getting a prediction, where we just train on some data and we test on some other data, and it's the kind of thing you can run very quickly. There's no validation. Okay, the coordinate system, yeah, so what happens here, so I've provided some functions at the top of this notebook to convert from the coordinates in this grid to longitude and latitude and back. So that's going to be part of the thing here. So you can take, if you know it's like the 100th pixel down and the 32nd pixel across, then you can put 132 into this and it will give you the position on the map. What's also here for you as you start playing around is most of this should work with just kind of Anaconda, like a basic, your basic installation. But if you install this library here, GDAL, then you can output the predictions as geotiffs. So if you want to take the output of that first very simple predictor and see what it looks like in QGIS, then you can run that code there. Yeah. Yeah, I mean, this basically is that. I mean, this is the same Python code that QGIS is built on. Oh, I mean, you could write all this as a plugin in QGIS. Yeah, absolutely. So all of this, if you finish prototyping in the notebook, then you can create a QGIS plugin which says like, input these shapefiles or these raster things here and like produce me the, click go and it gives you the other thing. Yeah, so absolutely, yeah. Just if we're doing things like assessing different prediction models, and certainly we want to go from this very simple one, which doesn't have any, it's not really a sort of spatial classifier. We want to go more into models which really kind of use like spatial principles to do their prediction, and testing those out. Like the QGIS interface probably isn't the easiest thing to do that with. If you want to see your ROC curve or like debug some of the variables or something, then maybe it's easier to do it this way. But it ports. It's the same code basically. And so what happens when you run this is you get like a geotiff file, and so if you want to actually have a look at the prediction, oh no, hang on. I have to actually train this. I think we should finish by actually looking at the deforestation forecast for East Africa. 2018. Yeah. Well, the last data we've got is 2016, so it's kind of the prediction for 2017. So when the data comes, then we can see. But I think what would be cool actually is like if people had different predictions, like based on this data, you could try tuning the models and trying different types of models according to what's in the practical, and come up with your best prediction of like what you think is going to happen like this year or has already happened last year. And then when this data set's updated, then we can have a look and see.
You might incentivize people to go and chop down loads of trees to prove their models.
Yeah, that's right. Okay, so that's our predicted one. This was a very simple one I was just testing code with. Let's try that again. Oh, what? It's not that. we go. All right, so okay, so we can see there, that's according to this quite simple model, like where it's predicted for the next year that there's going to be deforestation. And what we can do actually is like sometimes with these things you kind of need to see the context, right? So like there's a lot of this, it's not looking great for Western Uganda, I've got to say. So we can turn on a base layer and get some map context. Yeah, that's right, yeah. Yeah, we didn't include any information that this is a lake, right? Like, which would be another useful thing to, like, where's a water body, you know? Like, because, yeah, so it's, that's indeed reassuring, yeah. Okay, anyway, you can play around with QGIS and sort of, you know, explore where the areas are. But anyway, this is my forecast that, like, the sort of one of the most at-risk areas is this kind of, is that like Mitiana? Yeah, okay, so we'll wrap up there, and then I think let's take a break and, you know, oxygenate the, you know, the limbs and come back and do some practicals. So your turn. Okay, thanks very much.
Right, so I guess the field practical for this, we'll go to the conservancy and cut some trees.
Cut some trees.
Shira is not here. Get the bus, go cut trees.